Okay, guys, welcome. This is 11.2, second derivatives and graphs. Okay, so 11.1, we did first derivatives and their graphs. So we were able to sketch a function by the characteristics of the first derivative. Now we're going to sketch a graph by the characteristics of the first and the second derivative. So here's with the second derivative characteristics, it's called concavity. Okay, so the graph of a function f is concave upward on some interval ab if the first derivative is increasing on that interval. Okay. 2, the graph of a function is concave downward on some interval ab if the first derivative is decreasing on that interval. Okay, so second derivatives deal with concavity. Okay, first derivatives deal with maximums and minimums. So there's your difference right there. Remember, to determine where a function was increasing or decreasing, we took the derivative, we set it equal to 0, we solved for x, and we made a sign chart. Now we're going to do that with the second derivative as well. Okay, so here is our chart for concavity. Okay, so this says everything I just said above. If the second derivative is positive and the first derivative is increasing, this means the graph of the original function will be concave upward. Being concave upward looks like that. Second row, if the second derivative is negative, the first derivative is decreasing, which means the original function will be concave down. So this is concave down. Okay, so this is what we're going to be looking for when we make our sign charts. We're going to be looking for max and mins, we're going to be looking for concavity, and a bunch of other stuff, okay? All right. Important, it is important not to confuse concavity with falling and rising. A graph that is concave upward may be falling, rising, or both rising on the interval. Look at the first picture. This graph is concave up completely. So we see that it is first falling and then rising. So it is both falling and rising on the interval. And then 2, it is important not to confuse concavity with rising and falling. A graph that is concave downward may be rising, falling, or both rising and falling on the interval. That'd be picture 2. It is concave down completely. So this would be increasing, decreasing, rising, and then falls. Okay. And then let's say I had another graph that looks something like this. This would be concave down, which means here we're rising, and then this would be concave up. That's still rising. So, there you go. So it could be rising, rising, concave down to concave up. It all depends on your graph, okay? All right, so just drew that in there as an example, okay? Okay, let's get to it. Example 1. Determine the intervals on which the graph of each function is concave upward and the intervals on which it is concave downward. Sketch the graph. So we are given h of x equals x cubed. Find the second derivative. So find h double prime of x. So to get there, you know we first have to find the first derivative to get to the second derivative. So h prime would be 3x squared. H double prime would be 6x. That's what we're looking for. H double prime would be 6x. Oh, that made a nice box. Oh, never done that before. Oh well. Okay. Next. take the second derivative, set it equal to 0, and solve for x. Whatever we get for x, we will create a sign chart to determine the intervals of increase and decrease to find concavity. Okay? All right. So B and C are going to be worked together. Let's see. Yes. From the sign chart, determine the intervals where it's concave up and concave down. So for B, first thing we want to do, set it equal to 0. So H double prime of x equal to 0. This means 6x equals 0. Divide by 6, divide by 6, x equals 0. Okay. Oh, because I have that clicked on. Into shape. Oh, well, I accidentally clicked that button, but it seems to be working. Cool. All right. So what this means is that this now has a new name. Since it comes from the second derivative, this is called an inflection point. So second derivatives gives us inflection points. First derivatives give us critical numbers. Okay, all right, and there's a reason it's called inflection point, but we'll get there in a second. Okay, so now we create our sign chart. Negative infinity, positive infinity, I plot our inflection point of 0. Now my intervals, negative infinity to 0, 0 to infinity. Okay, test numbers. So intervals, test numbers. From negative infinity to 0, we pick -1. From 0 to infinity, we pick 1. Now, this is a sign chart for the second derivative. So we plug into our second derivative. So plug into the second derivative. Okay, so this means 6 times -1 gives me -6. And again, I don't care about the number that comes out. I only care about the sign. So this -6, so here we go. So from negative infinity to 0, this means that the second derivative is negative, which means the first derivative is decreasing, which means we are going to be concave down. That's all based on the chart on the first page. Okay. And then, maybe I can write that neater, right? Let's see. We're going to be negative, decreasing, and concave down. And then, plug in 1. 6 times 1 gives me 6. So this is positive, right? Positive, negative. That's all we really care about. Okay. So this means from 0 to infinity, the second derivative is positive, which means the first derivative is increasing, which means we are concave up. concave up. Okay, cool. Let me move myself up there. There we go. Okay, so that's how our sign chart for the second derivative works. This only looks for concavity, which means now we can answer C, because I said B and C go hand in hand. So looking at the sign chart above, it wants to know where is the original function concave up and concave downward. And all we have to do is state the intervals. So we are concave up on 0 to infinity. And we are concave down on negative infinity to 0. And all of this is based on that sign chart. Okay. Still going. Let me see. Okay, yeah, still good. Okay. Now it says sketch the graph. So like all the other ones, I'm going to take the original function, rewrite it. H of x equals x cubed. And the first thing I want to look for is x-intercepts. That's what we'll look for, x-intercepts. X-intercepts means you let h of x equals 0. So this means x cubed equals 0. And then I cube root both sides, and I get x equals 0. 0, 0. There's my x-intercept. Okay. And then if I wanted a y-intercept, just going to show the process. Y-intercept is going to give me the exact same value, but I'm going to still go through this process. Y-intercept, we let x equal 0, and this means I get h of 0, which gives me 0 cubed, which still gives me 0. Which that means that this becomes the y-intercept of 0, 0. Okay. So always important to know how to get an x-intercept and a y-intercept. Okay, so next is plotting. So we're gonna plot my x-intercept and my y-intercept, which happen to be at the same point, 0, 0. And now we are going to graph based on concavity. Let's see, that'll work. Okay, so it says that from negative infinity to 0, from negative infinity to 0, we are concave down. So what that means is that from negative infinity to 0, from the left side of the graph to 0, we are concave down. That's concave down. Let me write that on there. That is concave down. Because this is 0, right? And over here is negative infinity. So from negative infinity, we're concave down, just like our number line says. And then from 0 to infinity, we are concave up. I'm going to make it a little curve here. We are concave up. That's it. That's all. That's how we're going to graph. Okay. Perfect. That's graphing by concavity. Almost the same process as first derivatives, but this time you take the second derivative, you set it equal to 0, and you solve for x. Okay. All right. Now, finding inflection points. Well, it's a good thing we did that already. To find an inflection point, we take the second derivative, we set it equal to 0, and solve for x. Now, here's more definition on what an inflection point is. An inflection point is a point on the graph of the function where concavity changes from upward to downward or downward to upward. So in order to be an inflection point, concavity must change. So the concavity must change sign at that point. Okay, so if we look back at our last graph, well, 0 would be considered my inflection point because we went from concave down to concave up. So concavity changed. This means that 0 was my inflection point because concavity changed. Okay. Theorem 1, if f of c is an inflection point of f, then c is a partition number for the second derivative. Well, let's go back and look at the previous problem. Okay. We got that our inflection point was 0. And when we plot it on the number line, it breaks the number line apart, or it partitions the number line. So an inflection point can also be considered a partition number. Okay, that's all we're saying, nothing new. And this means that since concavity changed, our inflection point happened to be 0, 0. Which down here, f of c was my 0, 0. It was an inflection point because concavity changed, and 0, which is my c value, was a partition number because it broke up the number line. That's it. Simple. Well, I say it's simple, right? But all right, let's keep going. All right, let's do it again. Find inflection points. So find the second derivative, set it equal to 0, and solve for x. That's what we're going to do on example 2. So given f of x, find the second derivative, set it equal to 0, solve for x. This is us finding inflection points. These processes, pretty straightforward, right? Okay. So first derivative, 3x squared minus 12x plus 9. 3x squared minus 12x plus 9. Second derivative, f double prime of x, 6x minus 12. 6x minus 12. Okay, and then, not done. After we get the second derivative, set it equal to 0 and solve for x. We get 6x minus 12 equal to 0. 6x equals 12. Divide by 6, divide by 6. And x equals 2. This is my inflection point. And I'm going to say possible. Because in order for it to be an actual inflection point, remember, concavity has to change. Okay. Oops. All right, so 2 is my possible inflection point. And now we want to see where we're concave upward, concave downward. So we will make our sign chart and plot my inflection point. So there's my inflection point of 2, my possible one. And then here's negative infinity. There's positive infinity. Make my intervals. Okay. Negative infinity to 2. 2 to infinity. Pick test numbers. Negative infinity to 2, you can pick 1 or 0. 2 to infinity, pick 3. Now again, this is a sign chart for the second derivative. So plug these in to the second derivative. Okay, so my second derivative was 6x minus 12. So I'll have f double prime of 0 equals 6 times 0 minus 12, which gives me negative 12. And again, don't care about the number, only care about the sign. So here we are negative. This means that from negative infinity to 2, the second derivative is negative. The first derivative is increasing, which means we are concave up. All right, then f double prime of 3 gives me 6 times 3 minus 12. That gives me 18 minus 12, which gives me 6. And that's positive. So from 2 to infinity, the second derivative is positive. See, made a mistake already. But we'll continue with this. The second derivative is positive, which means the first derivative is increasing, which means we are concave up. Now, here's the mistake I made. From negative infinity to 2, we're not concave up, and we're not increasing. I don't know what I was thinking. Think it's my allergies. Ha. So, from negative infinity to 2, the second derivative is negative, which means the first derivative is decreasing, which means we are concave down. Sorry about that. Hopefully you caught that mistake. Okay, there it is, and we'll find out what intervals we're concave up and concave downward on. So I'll state those intervals just to say it. We are concave down on negative infinity to 2, and we are concave up on 2 to infinity. Okay. Now C. If x equals c is an inflection point, meaning the second derivative changed signs, then find f of c to get the actual inflection point, c. Oh man. Oh, c, f of c. Okay. So we look at our sign chart, and did concavity change? Did the signs change? Yes, we went from minus to plus. We went from concave down to concave up. This means that x equals 2 is an inflection point. is an inflection point. Okay. In IP. Which means that since it's an inflection point, we need to plug it back into the original function to find the exact point of inflection. So we take x equals 2, plug it into the original function f for f of 2. And now what is that function? There it is up there. So that'll give me 2 cubed minus 6 times 2 squared plus 9 times 2 plus 1. Calculate. Two cubed minus 6 times 2 squared plus 9 times 2 plus 1. We get 3. This means that my point of inflection is 2, 3. And that's what we're looking for, the point of inflection. POI. Okay. I guess to make a little side note, since 2 was an inflection point, plug into the original function. So I'll say that right here. Okay, there it is. So in order to be an actual inflection point, concavity must change. And if it does change, then we take that inflection point, which ours was 2, plug it into the original function, and this will give us the exact location of the inflection point, or the point of inflection. Yeehaw, right? Okay. All right. We've made it. Gonna take a small break. Hang on. Okay, I'm back. All right, so important partition numbers for the second derivative are only candidates for inflection points. That's why I said when we found x is 2 on the last example, it was a possible inflection point because we have no idea if concavity changes until we make that sign chart. Okay. The original function must be defined at x equals c, and the second derivative must change sign at x equals c in order for the graph to have an inflection point. So again, we find a possible point of inflection, we test it on a number line, and then we see if it's actual point of inflection. Okay, so that's what we're going to do again, but now we're going to graph this function x to the 4th minus 2x cubed by going over everything. This is called the graphing strategy. So step 1 is to find the domain and find the x and y intercepts of the function. Step 2 is everything we learned in 11.1. This says find the first derivative, set it equal to 0, solve for x, make a number line, find maxes and mins, find the exact location of the maxes and mins. So step 2 is everything we learned in 11.1. Crazy, right? One whole lesson in one step. Step 3 is everything we're doing today, looking for concavity, take the second derivative, set it equal to 0, solve for x, make a sign chart, find concavity, find possible points of inflection. And then step 4, graph it using all the information. And then, yeah, then we'll have one more left. So let's get started. Okay, analyze the function, find the domain and the intercepts x and y. So lucky, since you are business majors, you will only get polynomial functions. You won't get anything else that's difficult. You will only get polynomials. So with that being said, the domain should always be negative infinity to infinity. Only because it's a polynomial, right? Only because it's a polynomial. Okay, and now we find x-intercepts and y-intercepts. So x-intercepts, we let f of x equals 0. That looks like f prime, so let me fix that. Stop it. We let f of x equals 0. So we take the function x to the 4th minus 2x cubed, set it equal to 0. Factor x to the 4th minus 2x cubed, just making sure I have everything right. I can take out an x cubed, and that would leave me with x minus 2 equal to 0. Now, set these both equal to 0. X cubed equals 0. X minus 2 equal to 0. This would just be x equals 0. And this would be x equals 2. Which means that my x-intercepts are 0, 0, and 2, 0. Those are the x-intercepts. Okay. Y-intercept. Y-intercept, we let x equal 0. So f of 0 gives me 0 to the 4th minus 2 times 0 cubed. All of that just gives me 0. So my y-intercept is going to be 0, 0. Okay, first step's done. Domain, x-intercept, y-intercept. No calculus until now. Step 2. Everything we learned in 11.1, we apply to this step. We're going to take the first derivative. We're going to set it equal to 0. We're going to solve for x. We're going to create a number line. We're going to look for max and mins. We're going to find that max and min, plug it into the original function, and that'll give us the exact locations. Whew. And yes, it's a process, but that's one whole lesson put into one step. Crazy, I know. Okay. So let's find the first derivative. F prime of x. I'm going to get 4x cubed minus 6x squared. 4x cubed minus 6x squared. And then I'm going to set it equal to 0. Whoops, not like that. I'm going to set the derivative equal to 0. 4x cubed minus 6x squared equal to 0. And then solve for x. Greatest common factor, I can take a 2x squared out, and that would leave me with 2x minus 3 equal to 0. 4x cubed, 6x squared. Then set these both equal to 0. 2x squared equal to 0, 2x minus 3 equal to 0, and then this divide by 2, divide by 2, you get x squared equal to 0, which just gives me x equals 0. Here, 2x equals 3, x equals 3 halves, or better, 1.5. And guess what? Since this is the first derivative, these are called critical numbers. Okay, now what we do with those is we create our sign chart. There's negative infinity, there's positive infinity. Here's 0, here's 1.5, and make your intervals negative infinity to 0, 0 to 1.5, 1.5 to infinity. Pick your test numbers. X equals, X equals, X equals for the 3 intervals. And from negative infinity to 0, we'll pick negative 1. From 0 to 1.5, we'll pick 1. From 1.5 to infinity, we'll pick 2. This is a sign chart for the first derivative, so plug into the first derivative. And I'm going to do that really fast. Let me see. 4x cubed minus 6x squared. I type in negative 1, I get negative 10. 1, I get negative 2. And then 2, I get 8. There we go. Okay, cool. So again, we don't care about the number. We only care about the sign. Okay. So what this means is that from negative infinity to 0, we are negative. Here, let me just stand on this. There we go. From negative infinity to 0, the first derivative is negative, which means we are decreasing. The original function is decreasing. Then from 0 to 1.5, we are again negative and again decreasing. And then from 1.5 to infinity, we are positive and increasing. Okay. All that's left to do now, if I had space, is find the maximums and minimums. Okay, which means let's go ahead and look at 0. Let's look at 0. Well, we see at 0, we decrease and we decrease. So since there is no sign change, there is no max or minimum at 0. So 0 is nothing, right? So x equals 0 is neither. It's neither. Then we look at 1.5. We decrease and then we increase. We decrease and then increase. And if you remember, if you decrease and increase, this means that 1.5 is a minimum. Okay. Now, since we have a minimum at 1.5, we are going to take 1.5 and plug it back into the original function. This will give us the exact placement, the exact point of where that minimum is. So I'm going to say f of 1.5. And I'm going to take 1.5 and plug it into this original function. X to the 4th minus 2x cubed. 1.5 negative 1.6875. So just do that to 2 decimal places. Negative 1.63. Negative 1.69. So this means that at 1.5 and negative 1.69, we'll have a minimum. There you go. And that's what we're looking for. So everything we learned in 11.1, put into that one step. Crazy. And yes, we don't care about 0 because 0 was not a max or min, so there's no need to plug it into the original function. Good. Okay. Step 3. Everything we learned today. Take the second derivative now, set it equal to 0, solve for x, make a sign chart, pick test numbers, find concavity. So let's do that. So f double prime of x is going to be 12x squared minus 12x. Set that equal to 0. And solve for x. Factor out a 12x. That leaves you with x minus 1 equal to 0. Set both of those equal to 0. And we'll get 12x equals 0. X minus 1 equal to 0. Here, x equals 0. X equals 1. These are going to be called my possible inflection points. Possible inflection points. My pips. Okay. Sign chart. plot your inflection points, make your intervals, pick your test numbers. Three intervals, 3 values for x. Okay. Negative infinity to 0, negative 1. 0 to 1, 0.5. 1 to infinity, 2. This is a sign chart for the second derivative, so plug these in to the second derivative. F double prime of negative 1, F double prime of 0.5, and F double prime of 2. X squared minus 12x, okay, negative 1 gives me 24. 0.5 gives me negative 3. 2 gives me 24. Okay, let's relate those to the chart. From negative infinity to 0, we have a positive answer. So this means the second derivative is positive. The first derivative's increasing, which means we will be concave up. All right. The next one's negative. So from 0 to 1, we are negative, which means we are decreasing, which means we are concave down. And then last is positive, which means we're increasing, which means we are concave up. Perfect. Okay, almost done. Now we have to look at the chart for inflection points. Did concavity change on these possible inflection points? So we first look at 0. At 0, we go concave up to concave down, or we go increase to decrease, or we go plus to minus, which means concavity change. So this means 0 is an inflection point. I'll write that down here somewhere. X equals 0 is an inflection point. We'll come back to that. Now, let's look at 1. Is this now an inflection point? Did concavity change? Yes. We went from concave down to concave up. Or we went from minus to plus. The signs changed. Concavity changed. So this means that x equals 1 is also an inflection point. And since they are inflection points, we need to find the points of inflection. So take 0, take 1, and plug them into the original function. Plug into the original function. So what was my original function? There you are. X to the 4th minus 2x cubed. All right. Come back here, plugging them into the original. If I plug in 0, I get 0, which means 0, 0 is a point of inflection. If I plug in 1, I get negative 1, which means which means 1, -1. These are my points of inflection. All right, we have everything we need to now graph. Okay, so we have X-intercepts, we have Y-intercepts, I have my minimum, I have my points of inflection. Let's use all that information to graph. So let's first start with the X-intercepts and Y-intercepts. So X-intercepts are 0, 0, 2, 0, and Y-intercept is 0, 0. So that's what we'll plot first. Okay, and looking at my values, it seems that I can stretch this graph out. So I'm going to say 0, 1, 2, 3, 4, 5. Oops. -5, -4, -3. That's -1. That's -2. Good. And then I don't think we got anything larger than 5, so I think I can do the same here. 1, 2, 3, 4, 5. -1, -2. Yeah. All the way down there. Okay. Like I said, we're starting by plotting the X-intercepts. 0, 0, 2, 0. Y-intercept was also 0, 0, so that point's already there. Okay, step 1 is done on the graphing strategy. We plotted X-intercepts and Y-intercepts. Step 2, all we have to do is plot the only point we found. And the only point we found was that minimum of 1.5 and -1.69. That is ugly. But let's go find that graph. So 1.5 and -1.69. 1.5, -1.69, I'll put somewhere around there. There's the minimum. I'll even write that. This is the, work with me today, pen, work with me. That's the minimum. Okay? And then step 2 is done. We plotted the point from step 2. Step 3, plot the points of inflection. 0, 0, 1, -1. 0, 0 is there for us already. 1, -1, we'll plot. 1, -1, right there. Okay, and those are our points of inflection, so I'll do that too. That's our POI. Piece of inflection. Points of inflection. Come down. Okay. And now, the way we want to graph the rest of this is based on the sign chart for this second derivative. We're going to graph the rest of this by concavity. So, look at our number line, our sign chart in step 3. It says, from -infinity to 0, we are concave up. Well, what that looks like is we're going to start at 0 and go concave up. So I'm going to have something like that. That's concave up. And then look at the sign chart again. From 0 to 1, we are concave down. From 0 to 1, we are concave down. So that's just from 0 to 1. So this changes like that. That part is concave down. It may not look like it, but it's enough. Concave down. And then it says from 1 to infinity, we are concave up. So here's where we make the change. We now switch to concave up. And that's it. I'll put these points better. There you go. And that's it. That's how you graph by using the graphing strategy. Everything we've learned so far. Just follow the graphing strategy. Should be fine. Okay. Now we get to an application using all of this. The marketing research department of a computer company used a large city to test market the firm's new laptop. The department found that the relationship between price P, dollars per unit, and demand X, units per week, was given approximately by P equals 1296 minus 0.12x squared between 0 and 80 units per week. Okay. Revenue can be approximated by X times P, which you do X times 1296 X times 1296 minus 0.12x squared, distribute the X, and we get our revenue function of 1296 minus 0.12x cubed on the same interval, 0 to 80. Okay, so all this wants is for us to find the local extrema for the revenue function. Remember, extrema is just a fancy word for maximums or minimums, right? So local extrema means max or min. And now, remember to find maxes or mins, you take the first derivative. You set it equal to 0 and you solve for x. Create a sign chart and we'll find them. So let's do it. So we are taking the derivative of that function over there, 1296x minus 0.12x cubed. So r prime is going to be equal to 1296 minus 0.12. That's 0.36x squared. Then set it equal to 0. 1296 minus 0.36x squared equal to 0. And solve. This is going to use the square root method. So all I'm going to do is add 0.36x squared to the right side. And then I want to solve for x, so I'm going to divide by 0.36. 0.36. And I get 3600 equals x squared. Okay, now square root, and you get plus or minus 60 equal to x. Now remember, these are my critical numbers. Okay, number line time. Our number line is going to be different this time though, because they gave us x values to work with. Normally, our number line is from negative infinity to infinity, but now it's only going to be from 0 to 80. So when I make my number line, actually I don't even need the arrow there. Just put a stop here, stop there. There's 0, there's 80, and now if we look at my critical numbers, I have plus and minus 60. Well, guess which value we're going to use, and guess which value we're going to throw out. Exactly, you guessed it right. We're going to keep the positive 60 and dump the negative 60. So all we have to plot on my number line over here is 60. That's it. And it makes sense because if it's negative 60, this means we have negative items, and do we want that in our business? No, that's correct. Okay, so make your intervals. 0 to 60, 60 to 80. Pick your test numbers. 2 intervals, 2 x values. 0 to 60, we'll pick 1. 60 to 80, we'll pick 61. This is a sign chart for the first derivative, so plug these into your first derivative. R prime of 1, R prime of 61. Let me type that in, 1296 minus 0.36x squared. If I type in 1, I get 1295.6. If I type in 61, I get negative 43.56. Okay, now let's analyze our sign chart. From 0 to 60, we get a positive output. Remember, don't care about the number. I get a positive output. So this means that the derivative is positive, which means we are increasing. And then from 60 to 80, we get a negative output, which means that we are decreasing. Okay. So now we're looking for a local extrema. Find the local extrema for the revenue function. Well, we look at our only value of 60, which means that we increase and we decrease at that critical number of 60. Since we increase and decrease, this means that x equals 60 is a max. And if we want to find the exact location of that max, if we want to find the exact revenue at that max, take 60 and plug it into the original function. So we'll say R of 60. And I'll put a lovely little dollar sign there. And I'll have 1296 times 60 minus 0.12 times 60 cubed. And if we sell 60 units will make $51,840 in revenue. This means our maximum is at 60 and 51,840. There's that. Okay, there's the max. Okay, last one. On which intervals is the graph of the revenue function concave up, concave down? So we're looking for concavity, so you know that means to take the second derivative. So there's my first derivative, which means that for my second derivative, r double prime of x, I'm just going to get 6 times 2, negative 0.72x. And if we're looking for a concavity, you know, set your second derivative equal to 0, negative 0.72x equal to 0, divide by negative 0.72, negative 0.72, and x equals 0. This is my possible inflection point, the PIP. Now, make your sign chart. Again, we will use the same interval above. 0 to 80. Oh boy. Well then, look at that. Our possible inflection point is the starting point for our interval. This means our life is made easy because the only interval we want to deal with is from 0 to 80. Because if I use anything negative, well, we don't want anything negative because we can't sell negative items. So we keep it between 0 and 80. And all I have to do is pick one test number from 0 to 80. 79. Just kidding, 1. This is a sign chart for your second derivative. So plug this in to your second derivative. And if we plug that in, I get negative 0.72. Analyze the graph, the number line. This means that from 0 to 80, we are negative, which means the first derivative is decreasing, which means the original function will be concave down. That's all we're looking for. It says, where are you concave upward or downward? Well, only for this one, we can say that for the business model, we are concave down on 0 to 80. Concave down on 0 to 80. Okay, cool. All right. I mean, if you plugged in, if you did use something before 0, I'll just put this in green, you would be concave up on, negative infinity to 0, but that doesn't accurately model our business model. We don't want anything from negative infinity to 0 ever. So, erase that. So this is all we're looking for. Okay, that's it. is second derivatives in concavity. Of course, I'll send it to y'all.